Welcome to the Cosmic Classroom. Today we're going to be looking at the 2019 November Physics Paper 1. So let's get started. Question 1, fundamental SI units. So we need to consider each of these four and what their fundamental units would be. So we need, if we look up in the equation, we need to somehow get a division by a distance unit. We need to get a division by meters or meters squared if there's meters on the top, etc. We need some kind of division going on in order to get the meters to the -1. So with energy to the joule, we convert that using the work done equals force times distance expression, and force we convert from newtons to base units using F equals ma. There's not any division by any distance unit there, so it is not A. B is force, so that's just F equals ma again. Again, no division by a distance unit, we're not going to get the m to the -1. Momentum is mass times velocity. So kilograms meters per second, that is not correct either. So finally, pressure equals force over area. We're getting our division by our distance unit. So force is mass times acceleration, and area is area, so that is kilograms, acceleration meters per second squared, area meters squared. That's going to give us the necessary kilograms meters to the -1 seconds to the -2, so the answer is D. Question 2, two forces on a straight line, one's constant, one's proportional to velocity, so basically the varying force is a frictional force. As the speed increases, the frictional force is increasing. What's correct about the motion of the object? So we need to think about what's happening to the resultant force. So essentially, initially the resultant force is large and to the right, but then as the speed increases, that varying force to the left is going to also increase. So over time, our resultant force is going to get smaller and smaller and smaller until our resultant force is equal to 0. And at that point, it's going to be moving at a constant speed. So we're starting off with an initially large acceleration. That acceleration is decreasing over time until we get to acceleration equal to 0 once the two forces are balanced. So what is correct? The acceleration increases from 0 to a maximum? No. Initially, the resultant force will be the largest, so we'll have the largest acceleration at the start, and then it's decreasing. Acceleration increases from 0 to a maximum, that's the same one, so no. Velocity increases from 0 to a maximum. So yes, the velocity is going to be increasing. Initially, it is at rest. We've got an acceleration, so the velocity will increase. And we've basically got a terminal velocity situation going on here, where the air resistance is increasing until the two forces are equal and opposite, and we've hit our top speed and we no longer accelerate, so we're hitting a top velocity. D is incorrect because once the two forces are balanced, unless something else changes, then there's going to be no decelerating force. So the velocity is not going to decrease, we're just going to continue at our top speed in the same direction at a constant speed, constant velocity. Our resultant force is 0. So the answer is C. Question 3. A ball falls from rest in the absence of air resistance. We're looking at 1 second time intervals. What's the distance travelled in meters by the centre ball during each second for the first 4 seconds of the motion? So if we're in the absence of air resistance, A is constant, the acceleration is going to be constant, and it's going to be equal to G. So let's consider second 1. So what we're going to happen in second 1, so this is a suvat. So during the first second, we're after the distance travelled. It starts from rest. Acceleration is g, and it's taking 1 second of time. So using the s equals ut plus a half at squared expression, we're going to lose the front part of that, and we're just going to get a half times 10 times 1 squared. So in the first second, we're going to go 5 meters, right, which agrees with all of the answers, but what we're interested in is when it comes to doing the second and considering the suvat, we're no longer starting from rest. Okay, so we need to know U. We're after kind of like how far does it go, but we need to know what U is going to be. A is still G, and the time is still 1 second, but it's now already moving. So we need to know what V is going to be. So V is going to be U plus AT at the end of this first second. So U is 0. 10 times 1. So at the end of this first second, it is moving at 10 meters per second, and that is what we're going to need to work out how far it's going to go in second 2 to pick which of the answers is correct. But we can see we're on the right path, so that's the way to go because we are getting an answer that agrees with the answers that are available. So we're going at 10 meters per second now to start with. We're after how far does it travel in the second second. So again, S equals UT plus a half AT squared. But now we're not starting from rest, so 10 times 1 plus a half times 10 times 1 squared, and that comes to 15 meters. So the answer is B. You could carry on and check the third second to make sure you're absolutely sure, but 15 meters, that is different to the other 3, so B. Question 4, projectile, object thrown from a cliff at an angle to the horizontal. Right, so very basically, here is my cliff, here's the ground, and the projectile has been launched at an angle to the horizontal. So some angle theta. And we're performing projectile motion height of the cliff. We know the quantities. We know the horizontal component of the initial velocity. So we know U horizontal. We know the angle. We know the height of the cliff. What must we know in order to determine the horizontal distance? So to determine the range, what do we need to know to work out X? Well, the range is determined by the horizontal velocity and the amount of time that the projectile will spend in the air. But the amount of time that the projectile will spend in the air is determined by how long it takes it to perform the vertical part of the motion. So remember, time of flight, how long it spends in the air, that is determined by the vertical motion, how long it takes for it to go up and come back down again and reach the ground. And to work out the time of flight, we are going to need to know the height of the cliff, how long it's going to take it to come to the floor vertically. We will need to know the angle theta because we will need to work out the vertical component of the launch velocity, which we can get from UH and a bit of trigonometry. And we will also need to know UH, how far it's moving, how quickly it is moving in the horizontal direction to work out the range. So we are going to need to know all 3 of those quantities to perform our suvat calculations and work out the range. Question 5, we've got an acceleration time graph. What is the change in velocity? So the area under this graph is the change in velocity. The area under this graph is the change in velocity. So the area under this first section is 2 meters per second square. The area under the second section, trapezium, is 8 meters per second. So the total change in velocity is 10 meters per second for that particular motion. Question 6. Nuclear particle, 10 to the 8 electron volts, grain of sand, 32 milligrams. What speed must the grain of sand have for its kinetic energy to equal the energy of the nuclear particle? So, kinetic energy question. So, EK equals a half mv squared, but we've got a lot going on in this question in terms of the units. So, the kinetic energy is given in electron volts. We need it in joules. So we've got a 1 times 10 to the 8 electron volts. Converting that to joules, we multiply that by 1.6 times 10 to the minus 19. We then have the half. Now, this is the one to watch. The mass here is given in grams, not kilograms, and it is milligrams. So this is conversion from milligrams to grams, 10 to the minus 3, and then conversion from grams to kilograms, another 10 to the minus 3. So this is actually 32 times 10 to the minus 6 milligrams, and then grams to kilograms. We're trying to work out what speed we need in order to have that 10 to the 8 electron volts. So on the left-hand side, 10 to the 8, 10 to the minus 19, that gives us 1.6 times 10 to the minus 11. And the half times 32 times 10 to the minus 6, that becomes 1.6 times 10 to the minus 5 v squared. I've put it 1.6 so that my division is going to be easier. In the next step, I've got 1.6 and 1.6 and just two differing powers of 10. So I've got 1.6 times 10 to the minus 11 divided by 1.6 times 10 to the minus 5. So that is 1 times 10 to the minus 6 is v squared. And then the square root of that is 1 times 10 to the minus 3 meters per second equals v, and 10 to the minus 3 is milli, so that is 1 millimeter per second. So the answer is A. Tension in a horizontal spring directly proportional to the extension. The energy stored at extension x is E. What is the work done when its extension changes from x to x over 4? So it's force proportional to extension. It's obeying Hooke's law. Energy equals a half kx squared. So the work that is done, that's the change in energy that has been performed by the spring. Right, so we need to look at what the energy expression is when the spring's at x and when it's at x over 4. So when it is at x, the energy stored is a half k x squared. When it is at x over 4, the energy stored is a half k x over 4 all squared, and that is 1 over 16 of a half k x squared, and this is our original amount of energy stored at x. So if that is kind of our E1 and this is our E2, that is 1/16 of the energy stored initially at E1. So we've gone from there being a certain amount of energy E1. When it's come to x over 4, there is now a new amount of energy that is equal to 1/16 of E1. So the amount of work that has been done by the spring has changed the energy from a certain amount, a total amount, E1, to 1/16 of that amount. So 15 over 16 of the original energy has been transferred away. We now have 1/16 of the energy remaining. Therefore, the answer is D. That is the energy transferred. We've lost 15 over 16 of the original energy. That's the work done. Question 8. Mass of water is at a temperature of 290 Kelvin. Specific capacity of water is C. We've got ice at the melting point, so at 0 degrees. It's added to the water, reduces the water temperature to freezing point, so down to 0 degrees as well. Specific length of heat of fusion is L. What's the minimum mass of ice that is required? So we've got ice going into water. The ice is going to melt. The water is going to provide the energy for that melting to occur. So the energy lost by the water is going to cool down. The energy lost by the water is equal to the energy gained by the ice whilst melting. So the water is just cooling down, it's not changing state, so that is specific heat capacity, so the mass of the water, C for the water, delta T for the water is equal to, and then the ice is at melting already, it's at 0 degrees already, 0 degrees Celsius. It's just changing state because the water is coming down to freezing point, so we're not increasing the temperature of the ice at all, staying at the same temperature, and it's just melting. So the mass of the ice times the latent heat of fusion for the ice. So rearranging that, that's the mass of the water. So we're after the mass of the ice. So the mass of the water is just M, the specific heat capacity of the water is C. Delta T for the water. Now this is where we need to be careful because we are given the temperature of the water in Kelvin, not degrees C. So the change in temperature is not 290. That would take it down to 0 Kelvin, which is absolute zero, which is not what we're trying to do. We're just trying to get it down to 0 degrees C. So 290 Kelvin is 17 degrees C. So the change in temperature of the water is just 17 degrees, either Kelvin or degrees Celsius. Delta T is 17. We're dividing that by L, and that is equal to the mass of the ice. So the answer is A. Question 9. Under which conditions of pressure and density will the real gas approximate to an ideal gas? So in an ideal gas, the particles are taking up a virtually non-existent amount of the volume of the actual volume of the gas. So we need the gas to take up a large amount of space, and the particles to be incredibly spread out within that. We also need there to be virtually no forces of attraction between the particles in the gas. So again, we need them to be incredibly well spaced out, very far apart from each other. So the scenario in terms of pressure and density that's going to achieve that, just have a large volume where the particles take up hardly any of that volume, and for the particles to be so far apart we can ignore the interparticle forces. We need the pressure to be low and the density to be low. If either of those two things are high, we're compressing the gas down into a much smaller volume. The particles will take up a more significant amount of the volume and they'll be closer together, meaning the forces between them will be more significant as well. So we need all the particles really far apart, low pressure, low density. 2 flasks, P and Q. We've got an ideal gas. They're connected with a tube, negligible volume. Volume of P is twice the volume of Q. We've got the temperature of P and we've got the temperature of Q. We want what is the mass of the gas in P and the mass of the gas in Q. So the gas is the same throughout both containers. The thing to appreciate here is that the pressure is the same throughout the entire system. So the pressure is equal throughout. So P and Q have both got the same pressure inside them. They've got different volumes and different temperatures, but the pressure is the same. They're connected. Pressure is the same throughout a fluid, a gas in this case. So we can consider an equation for P and an equation for Q. We're going to go with the PV equals nRT. We're after the mass of the gas in P, mass of the gas in Q. That's going to come from N. So N is mass over molar mass. So we'll come back to that later. So if we consider gas P and container P, container Q, consider the gas in both. So in P, we've got pressure, we've got the volume in P, we've got the number of moles of the gas in P, and we've got R constant, and we've got the temperature in P. And then for Q, we've got the same pressure, we've got the volume of Q, number of moles contained within Q, constant R, and the temperature in Q. Let's put some numbers in. We've got some values in terms of volume of P is twice that of Q, and we've got some temperature values. So for P, well, hopefully I'm actually going to get rid of some terms here. Hopefully you can see that when I come to do a division, I'm going to lose pressure and the gas constant because they're constant within each. So let's get rid of those and make this a little bit easier to work with. So the volume of P is twice the volume of Q, and the temperature in P is 200 Kelvin. And the volume of Q is just the volume of Q, and the temperature of Q is 400 Kelvin. Slight rearrangement. Let's move the 200 and the 400 underneath the volumes, because if I'm looking to consider how the masses are related to each other, I'm looking at the number of moles based on mass over molar mass that we had earlier. So we're going to have that is equal to the mass in P over the molar mass, and this is equal to the mass in Q over the molar mass. So both of these are going to have molar mass in their expressions. Take that away off the bottom of the fraction. Move it up to the side. So we're doing mass of P over mass of Q. I mean, some of you may have already spotted that actually I can get rid of the molar mass as well. They are also going to cancel. But I'm going to have mass of P, which is 2 VQ molar mass over 200, and then mass of Q is VQ molar mass over 400. Fraction on the bottom of a fraction, flip and multiply. So we've got 2 VQ MR over 200. The fraction on the bottom flips and multiplies, so now I've got 400 over VQ MR. So I can lose the VQs and the MRs, VQs and the MRs. I'm going to get 2 times 400, which is 800, over the 200, which is 4. Transverse wave. So we've got a displacement distance graph. We've got frequency is 25, speed is 100. What is correct for this wave? So the particles at x and y are in phase. No, they are not. One's at maximum positive displacement, one's at maximum negative displacement. They are not at the same point in their oscillation. A is incorrect. Velocity of particle x is a maximum. X is at maximum displacement. It's at the amplitude of its oscillation. If you think about a pendulum swinging, when it's at maximum displacement, it has 0 velocity, so that is not correct. Horizontal distance between x and z is 3 meters. Need to know what the wavelength is in order to work that out. So I need to know what lambda is for the wave. Thankfully, I can work that out. I've got the frequency and the speed. So we know that lambda is v over f, so 100 over 25. So lambda is 4 meters, x to z is 3/4 of a wavelength. So x to z is going to be 3 meters. So C is indeed correct. Let's just double check D. Velocity of the particle at y is 100 meters per second. Well, y is at maximum negative displacement. Same argument as for x, but it's at the negative displacement this time. When it's at the maximum amplitude, its velocity is 0. So that is also incorrect. The answer is C. Question 12, we've now got a displacement time graph. What are the frequency and amplitude of the oscillation? So amplitude, we can just read off the graph. It is the height, the maximum displacement from the equilibrium position. Check the scale, 10 to the minus 6, so it is 2 micrometers. So we're either going for A or C. It is not B or D. What is the frequency? Well, we can read from the graph the time period of the wave. So it starts here, so we can read the time period of the wave from this graph. It is 20 times 10 to the minus 6. So we can do F is 1 over T. It's 1 over 20 times 10 to the minus 6, or 1 over 0.2 times 10 to the minus 4. F therefore is 5 times 10 to the 4 hertz, or 50 kilohertz. The answer is C. Question 13, we've got two polarizing filters. They arrange so the light emerging from Y has a maximum intensity. So if the light emerging from Y has a maximum intensity, both of the filters must initially be set so that their polarizing directions are the same. So for the sake of argument, let's say that X is a vertical polarizer. If we're getting maximum intensity out of Y, that must also be arranged in a vertical polarization position so that everything that goes through X also goes through Y. That's the most we're going to get out at the end. What are the first three successive values of theta for which we're going to get another maximum? Well, the only time we're going to get a maximum is when both filters are orientated in the same direction. So if this is our initial setup when theta is 0, we're going to have to rotate through 180 degrees until Y is back to being in a vertical setup again. If we went to 90 degrees, Y would be in this direction and nothing would pass through Y. That would be a minimum. So we need to go around so that Y is back to a vertical direction. So it is not A or B. But then if we look, we only need to go 360 degrees to get the next maximum. If that's our 90 degree turn and that's our 180 degree turn, our 270 would then be back to a horizontal, and then our 360 would be back to a vertical. So it is 180 to 360 to 540 and so on. Question 14, standing wave question. Pipe of length 0.6 metres, filled with gas and closed at one end. Got speed of the sound is 300. What are the frequencies of the first two harmonics? So let's consider harmonic number 1. Okay, our first harmonic looks like this in a pipe closed at one end. We've got a 0.6 metre tube. So that 0.6 metres is giving us a quarter of the wavelength. I find these sorts of questions, it's just easier to work in fractions than it is in decimals, with this being a non-calculator paper. So that is 3/5 is equal to a quarter of lambda, or lambda is equal to 12/5 metres. We can then work out the value of F from V over lambda. So V is 300 metres, lambda is 12/5, which gives me 5/12 multiplied by 300. You can do the multiplication and the division on that, and that is 125 hertz. So it is A or B. Quick check then on the second harmonic. So the second harmonic will just add a node. So we now have 3/4 of a wavelength for the 0.6 metres. Same thing to fractions. We've now got 3/4 of a wavelength is equal to our 3/5 metres. So we end up with lambda being equal to 4/5 metres this time, once we rearrange those fractions. And then same thing, F is 300, but this time over 4/5, which is 5/4 times the 300. Do the multiplication and the division, and that is 375 hertz. So the answer is B. Question 15, we've got a negatively charged particle in a uniform gravitational field positioned midway between two charged conducting plates. The PD is changed until the particle is held at rest. So if it's being held at rest, we've got two forces working on it here. We have the weight of the particle acting downwards, and then we have the force from the electrical attraction to the positive plate acting upwards. Now F is equal to EQ, so it's equal to the strength of the field multiplied by the charge, and obviously the weight is equal to mg. What change will cause the particle to accelerate downwards relative to the plates? So decreasing the charge on the particle. So if we make Q smaller, that is going to affect this expression. If we make Q smaller, the electric field's still the same, so the upwards force will decrease. That will mean that the weight force downwards will be larger than the force from the electric field upwards, so that would cause the particle to accelerate downwards. So A is correct. Let's just quickly run through the other three to make sure we're happy with our choice. We have decreasing the separation of the plates. It's a parallel plate system, so E equals V over D for a parallel plate system. So if we make D, the separation of the plates, smaller, that would make the electric field larger. That would make the force upwards due to the electric field larger. So that would actually cause the particle to move in an upwards direction. So it's definitely not B. C, increasing the length of the plates. That has no impact on any of our equations. It doesn't change the charge, it doesn't change E, it doesn't change the weight. It's irrelevant in this scenario. Increasing the potential difference between the plates, well, that would also affect our E equals V over D. That would make V larger, which would make the electric field strength E larger, which would make the force upwards due to the electric field larger, and the particle would move upwards again, so it's also not D. So we are correct that the answer is indeed A. Question 16, we've got two power supplies, one fixed, one variable. We've got two resistors, 9 ohms, 3 ohms. And the variable resistor P is varied such that the reading on the ammeter is 0. So we're not reading anything on the ammeter, no current is flowing through that section of the circuit. Well, if no current is flowing through that section of the circuit, that means that this circuit just becomes this. This is the direction that the current is flowing, just through the two resistors. Nothing's going through the variable power supply. And it wants to know, what is the value on P for that to occur? Well, if we've just gone down to no current going through P, then it's basically acting like an ideal voltmeter. No current is flowing through that section of the circuit. So what is the reading that we're going to get? At that point, the current's just going straight through the 3 ohm and the 9 ohm resistor. So this just becomes a V equals IR problem. You can do it in the ratios, but the current in the circuit then is 24 over the total resistance, 9 plus 3. So the current in the circuit is 2 amps, and that gives a value across the 3 ohm resistor of just 2 times 3 of 6 volts. So we need 6 volts across there if there's going to be no current flowing through that section. Essentially, if the ammeter is 0, it's behaving like an ideal voltmeter. We're just taking a voltmeter reading. Question 17. Wire placed in a magnetic field experiences a force. What is the direction of F? So this is Fleming's left-hand rule. The size of the force is given by BIL sine theta. So the direction of the force, if we think about Fleming's left-hand rule, you've got your thumb is the direction of the force, your index finger is the direction of the magnetic field, your middle finger is the direction of the current. So A is incorrect, B and I, the magnetic field and the current, both contribute to the direction of the force, so therefore B is also incorrect. If you look at your 3 fingers, if you're holding them out in your Fleming's left-hand rule orientation, they're all at 90 degrees to each other. So I and B, so your index finger and your middle finger, are on the same plane, but they're at 90 degrees to each other. So they are kind of like on the same page, but they're at 90 degrees. Your thumb is definitely not on that same plane. It's then in the kind of Z direction, if you like. So it is not C, but your thumb is at 90 degrees to the plane, the page, the direction that your finger and your first finger and your middle finger are in. So it is D. So it's just the orientation of your fingers in Fleming's left-hand rule and knowing what they stand for. Question 18. Object moving in a circular motion hung by a string. String makes an angle theta with a vertical. The angular speed of the object is omega. What is tan theta? So we have to do something with the angles here. So I'm just going to mark on some values. So we've got the tension in the string. We've got the weight of the object. if I stick the vertical in there, this is also theta, and my centripetal force is acting in towards the centre of the circle. So if I look at my answers, everything's got an omega in it, and the mass has disappeared. So think about kind of some of the expressions I've got going on here. The centripetal force is being given by the horizontal component of the tension, T sine theta, and the mass, so vertically we've got balanced forces. So vertically I've got the mass, the multiplied by g, the weight is being balanced by the vertical component of the tension, T cos theta. So that's kind of my starting point. I'm just looking at what forces have I got, what expressions have I got. So I've got a sine and a cos, so we can definitely do something in terms of finding tan theta. I need to replace the centripetal force, Fc, with an equation. If we look on the data sheet, Fc is m omega squared r. So I can say that m omega squared r is equal to t sine theta. And then I can use this expression here, because if I look at all my answers, mass is not contained in any of my answers, so I can use the mg equals t cos theta to replace m on the left-hand side of this equation. So I can have that t cos theta over g omega squared r equals t sine theta. And then to get tan theta, I need to do sine divided by cos. So I'm going to have t omega squared r g equals t sine theta over cos theta, which is my tan theta. The t's are going to cancel. I'm left with omega squared r over g equals tan theta, which is A. Question 19. Got nuclide X, a couple of decay routes, alpha then beta minus or beta minus then alpha, and we're asked which statement is correct in terms of mass numbers, atomic numbers being the same isotopes, different isotopes, so we need to think about how the numbers are changing. So I'm just going to assign some random numbers to nuclide X. Let's make it 10 and 8, so I've got kind of enough numbers to play with in terms of the two decays. So after an alpha decay, P will then have numbers 6 and 6, so it'll have lost 4 nucleons to protons. And then beta minus, it's gaining a proton, maintaining the same neutron turning into a proton containing the same number of nucleons. Or that's gone a bit weird, hasn't it? Doesn't matter, let's check on the numbers. R is then going to be 9 and 10, and S will then be same, slightly weird, 6 and 7. Probably should have given nuclide X 11 nucleons. I know that physically doesn't work, but it's worth it just for checking on the numbers. Q and S are different isotopes of the same elements. Q and S both have the same number of nucleons. I know it's not an actually physically possibly same number of nucleons, but no, that's not true. Doesn't work. Mass numbers of X and R are the same. X and R have the same mass number of 10. Yes, that is true. Atomic numbers of P and R are the same. No, that is not true. One's got 6, one's got 9. X and R are different isotopes of the same element. No, they've got different atomic numbers. So that is also not true. You could have done that algebraically and then you wouldn't have had the slightly weird numbers that I had, but it works. Question 20. Which of the proton, electron and the alpha particle at rest have the smallest and largest charge to mass ratio? So charge to mass ratio, charge to mass ratio. So for the alpha particle, that is 2/4. For the electron, that is 1/, and then it depends how you want to do the electron, 1/2000 or 1/860. It's tiny. That's going to be pretty big. and then the proton is 1 over 1. So the alpha is going to be the smallest at 2 over 4. The electron, that's going to end up being, 2000, it's going to end up being the largest. So the answer is A. Gamma radiation is deflected by a magnetic field. No, it has no charge. We need charge to be able to be deflected by a magnetic field. Affects a photographic plate. Yes, it does. So that's a possibility. Originates in the electron cloud outside a nucleus. No, gamma radiation from nuclear decay that originates inside the nucleus is deflected by an electric field. Again, no, because it has no charge. So the answer is indeed B. Okay, question 22. Equations of motion for uniform acceleration apply to all accelerations. No, they do not. Acceleration has to be constant. Cannot be proved mathematically. Yes, they absolutely can. Relate force to other quantities in mechanics. Well, force is not part of the uniform acceleration equations of motion. Were developed through observing the natural world. Yes, they were. What are the units of specific energy and energy density? This is a knowledge and definitions question. This is something you should know. So specific energy is joules per kilogram, so B or C. And then energy density is, think about density. Density is mass over volume. It's the energy per volume of material that you're using. So joules per meter cubed. So that is B. Question 24, function of a moderator in thermonuclear fission. This is also knowledge. This is a GCSE knowledge question. We should know what a moderator does. It slows the neutrons down so that they can be absorbed by another uranium nucleus. So it's decreasing the kinetic energy of the neutrons. A. And then question 25 is another knowledge question. We have a page of knowledge questions here. Average albedo of the moon. If you go to topic 8.2 in your data booklet, you will find the equation for albedo, total scattered power over total incident power. So if it's 0.1, that means that 10% of the radiation incident on the moon is reflected by its surface. So it's scattering 10% of the 100% that is coming in to get an albedo of 0.1. Question 26. Object undergoes simple harmonic motion, amplitude x0. When the displacement is x0 over 3, the speed of the object is v. What is the speed when the displacement is x0? Now, careful, read the question. If you go to the data booklet, you'll find this equation. And then hopefully you'll very quickly realise that if you stick x0 into there, you're going to get an answer of 0. But if you think about it, the amplitude is x0. What's the speed when the displacement is x0? Doing SHM when we're at maximum displacement, the velocity is 0. Light of frequency 500 terahertz, incident on a single slit, forms a diffraction pattern. We've got the angle of the first minimum. We're then changing the frequency to 715 terahertz. What is the angle now to the first diffraction minimum? So if we go to our data booklet, the equation we're after is this one, theta equals lambda over B. This gives us the angle to the first diffraction minimum for a single slit. B is the width of the slits. Obviously, we're not dealing with lambda here, we're dealing with frequency. So this is our initial expression for theta. So initially, theta is, let's change this to a frequency expression. So C over F over B. So just from V equals F lambda. So that's C over F times B. So theta is proportional to 1 over F. So we've now, for our new scenario, for our new theta, dealing with the 1 over F proportionality, we've gone from 500 terahertz to 750 terahertz, so we've increased this to 1.5 F. Therefore, we are dealing with a 1 equals 3 over 2 F, so 2 over 3. So we're dealing with a 2 over 3 change to our original expression of 1 over F. So our new theta is going to be our original theta times 2/3. So it's 2/3 times 2.4 times 10 to the minus 3, which gives us 1.6 radians. Light of wavelength lambda, instant on a diffraction grating of spacing 3 lambda. What is the angle between the two second order maxima? So this is our n lambda equals d sine theta expression. We're doing the second order, lambda is lambda, d is 3 lambda, sine theta. So that gives me 2 over 3 is sine theta, or theta is sine to the minus 1 of 2 over 3. But this is the angle between the centre, so this is my centre line, here's my first order, here's my second order, this is the angle here, and the question asks for the angle between the two second order maxima. So what is the total angle? So I'm going to have to do theta times 2, so it's going to end up being 2 sine to the minus 1 of 2/3 if this is my first order and this is my second order. So C. Question 29. Sea waves move toward a beach, constant speed of 2. They arrive at the beach with a frequency 0.1. We've then got a girl on a surfboard moving at right angles. She observes a frequency of 0.4. So this is a Doppler effect question. We have a moving observer. So the girl is moving in the sea at right angles to the wavefronts. What's the speed of the surfboard? What is the direction of motion? So we have got an observation of a higher frequency than the actual kind of emitted frequency. Therefore, the waves must be going towards the girl on the surfboard. So if the wave direction is to the left, the girl on the surfboard must be moving to the right. So if we do the speed of the observer, the girl on the surfboard is moving to the right so that the waves are coming towards her so that she can appreciate a higher frequency. The waves get compressed as they approach her. So she's moving away from the beach, so B or D, and then we just need the speed. So if we go to our data booklet, we've got moving observer, so it is F prime, so the observed frequency is the emitted frequency, and it's V plus or minus the speed of the observer over the wave speed. We're observing a higher frequency, so that means we're going to be doing a plus on the top of this fraction so that we get an observed frequency that's larger than the emitted frequency. And we can put some numbers in. So our observed frequency is 0.4, emitted is 0.1, speed of the wave is 2. We want the speed of the surfboard 2. Rearranging that, so it's 4, 2 plus speed of the observer over 2. So that's be 4 times 2 is 8, minus 2 is 6, is our speed of the observer. So the answer is B. Question 30. Gravitational potential is V at distance r above the surface of a spherical planet of radius r. Uniform density, we go to a distance 2r above the surface. What is the gravitational potential? So again, this is a change some variables. How does it change to our original? So find the initial algebraic expression, do the new algebraic expression, try to factorize out your original algebraic expression, get your multiplier. So initially, we've got planet, radius r, and then we're at a distance r away, then same planet, radius r, but then we go to a distance that is 2r away. So my v initially is equal to minus gm over r. This case is 2r to the centre of the planet. Then my v kind of new scenario is now minus gm over 3r. So I need to find this expression in my new expression and factorize it out. So if I factorize out minus gm over 2r as a factor, I would need to multiply that by 2 over 3 to get me my minus gm over 3r equation for my new system, and that is my initial v. So the new potential is 2/3 of the original potential, which is D. Force between 2-point charges. This is the same sort of question. Separation of the charges is x. What's the force when the separation is increased to 3x? So this is the F equals KQQ over r squared. equation. So we should be happy with the fact that F is proportional to 1 over r squared. So if I go from x to 3x, I'm going from x squared to 9x squared. So I'm going to the force being 1/9 of the original force. We should be happy with that as a 1 over r squared relationship. We go 3 times the distance, we get 1/9 of the force. Electron enters a uniform electric field E with a velocity v. What's the path of the electron after entering the field? Now, the answer to this is parabolic. And the analogy I'm going to use is a projectile moving through a gravitational field. If I have the ground and I launch a projectile with speed v in a constant gravitational field, I get a parabolic path. And we're getting exactly the same thing with our electron entering our uniform electric field. We have constant field, velocity v, we're going to get exactly the same motion, just with a different field causing the force. It is parabolic. So the analogy is what would happen to a mass moving in a constant gravitational field. It would follow a parabolic path. It's the same physics, just slightly different equations. Question 33, we've got 2 coils. The one on the right has a constant current, we're shown the direction. X moves towards then away from Y. What is the direction of current in X relative to that in Y? So this is induced current in X due to its motion in a field provided by Y and a little bit of Lenz's law. Okay, so if we use the right-hand grip rule on the coil on the right-hand side, we see that the field on the right-hand side is going in this direction. It would be going in this direction through the middle. So as X is moved towards Y, a current is induced, a field is induced. The direction of that field will be such that it's trying to repel itself from Y. So Lenz's law, it's trying to oppose the change that caused it. The change was bringing it close to Y, so it wants to repel itself away from Y. So we need a field when X moves in this direction. We need the field produced in the centre to be opposing the field of Y. So again, get your right-hand grip rule out. In order to get the field going in that direction, the current needs to be going this way round the loop in order to give us the right field direction. So when it moves towards Y, the current is in the opposite direction in order to oppose the field. Then if we do the same consideration on the way out, when it moves away from Y, same argument applies, it's moving away from Y. The change is that it's moving away from Y, so it wants to be attracted back towards Y, so we need the field to be attracting towards Y. So in that scenario, the current needs to be in the same direction to get an attractive field rather than a repulsive field. So the current would be in the same direction as Y. So the answer is C. So we've had to combine right-hand grip rule with a bit of Lenz's law and induced EMF in question 33. Question 34. Again, we've got an induced EMF. What's the possible relationship between the flux and the induced EMF? So the induced EMF, if we look at our data booklet, is equal to minus n delta phi over t. So as the flux changes, the EMF is equal to the negative of the rate of change of flux. So the EMF is a maximum for the maximum change in flux, but opposite in direction. So when the flux is not changing, the EMF is 0. When the flux is changing, the EMF is a maximum. So essentially, the EMF graph is the gradient of the flux graph. So if we look at A, the flux here has got its largest change. It's the biggest rate of change of flux, steepest gradient, but the EMF is 0. Well, that doesn't work. We said the bigger the change in flux, the bigger the EMF, so that is incorrect. For B, again, let's look at a flux point. So let's take this point here. The flux is having the largest change in the positive direction, so that means the EMF will be a maximum but opposite. So if we've got positive changing flux, we have maximum negative EMF, which we do. Then let's check this point up here. The flux is not changing. The rate of change of flux there is 0. The gradient is 0. The EMF is also 0. B does work. Let's just have a quick check of C and D. Same thing. Let's do a flux. So this is positively changing flux. So that would give a maximum negative EMF. Nope, it's given us maximum positive EMF. So C is not correct. And then double check of D. Well, I can already see that when the flux is at maximum change, the EMF is at 0, which is incorrect. So it's definitely not D, so B is the correct answer. 35, capacitor, capacitance 1 microfarad, stores a charge. The capacitor is discharged through a 25 ohm resistor. What's the maximum current in the resistor? So we're going to get the maximum current when we've got the maximum voltage and the maximum charge. So if we look at what the maximum value of V is going to be, that is Q over C when we've got our maximum charge stored. So 15 times 10 to the minus 6 over our 1 microfarad, 10 to the minus 6. So that gives us a maximum value for the voltage of 15 volts at the maximum charge stored. And that's going to give us a maximum current then of V over R using our maximum voltage. So 15 over 25, 3 over 5, or 0.6 amps. So C. Question 36, diode bridge rectification. Alternating PD applied between M and N. 3 statements are given which are correct. So when diode P conducts, Q does not conduct. So if we think about, there are 2 possible paths through this diode rectification bridge depending on the direction of current flow, whether it's going from N to N or N to M. So if the current is flowing in this direction, we're going up through R, through the resistor, through P and out. If the current is flowing from M to N in this direction, we're going down through Q, then through the resistor, through S and out to N. So we've got 2 possible current paths: up through R, through the resistor and out, down through Q, through the resistor and out through S. So when diode P conducts, Q does not conduct. So if P is conducting, Q is not conducting. That is correct. When diode S conducts, neither P nor R conducts. So if S is conducting, P and R are not, they're not on the same path. That is also true. Direction of current in the resistors from left to right. Well, no, if we look, both times the current has gone from right to left. That is not correct. So 1 and 2 are correct, only looking at the 2 possible paths for current to flow. So A. Question 37, an electron of low energy is enclosed within a high potential barrier. What is the process by the electron can escape? This is a knowledge question. We're in a potential well. The electron's down here. It doesn't have enough energy to get out. How can it get out? Well, it can behave like a wave and it can quantum tunnel its way out to the outside. So A. Question 38, monochromatic radiation made up of photons each of momentum P. The intensity of the beam is doubled without changing the frequency. What is the momentum of each photon after the change? Well, photon momentum is given by h over lambda. It depends on the wavelength of the wave and h Planck's constant. So if the frequency is not changed, the photons are still exactly the same photons. They have the same amount of energy, they have the same amount of momentum, there are just more of them, but their individual properties are still identical if the frequency has not changed. So the momentum is still p. There are more photons, but the properties of the photons have not changed if the frequency has not changed. Behaviour of electrons. Which of these are evidence that the electron behaves as a particle? So electron emission as a result of a photoelectric effect, the electrons are behaving as particles in that scenario. They absorb a photon, they're emitted as a particle from the surface. Electron diffraction, well, diffraction is wave behaviour, that is not particle behaviour. Emission of radio waves as a result of electrons oscillating in a conductor, that is electrons moving up and down between energy levels and emitting photons, that is then behaving as particles and emitting photons, so it is 1 and 3. And lastly, question 40. Radioactive sample contains n0 atoms at time 0. At time t, there are n atoms remaining. Half-life is t over half. What is the decay rate of this sample proportional to? So the decay rate is the activity A. So if we look at the equations we've got on the data booklet, we've got n equals n0 e to the minus lambda t. And we've got A equals lambda n0 e to the minus lambda t. Well, this is n. So the activity, the decay rate, is equal to lambda n, or A is proportional to n. Lambda is the decay constant, which is linked to the half-life, so that is fixed, so A is proportional to n, which is answer number A. And there we have it, we're at the end of the paper. I hope that you have found that helpful, and as always, good luck with your remaining revision.